Okay, so a typical use of our derivative is to solve what we call maximum minimum problems. So as soon as we see any scenario where we need to find a maximum or a minimum value, by definition, that's where the gradient is zero. Okay, so it means it implies to us then, if we have to find a maximum or a minimum, we're probably going to need to find a derivative. Okay, so let's have a look. The canvas shelter is made up with a back, 2 square sides and a top. The area of canvas available is 24 metres squared. Find the dimensions of the shelter that will create the largest possible volume. So we've got the volume of like a box really, isn't it? So we know that volume is equal to length by width by height. Okay, and in this case, we've got x by y, which is equal to x times x times y, which is equal to x squared y. Now the problem we've got there is that we've got two variables still. So we need to find some relationship between x squared, or between x and y. So what information haven't we used yet? We haven't made use of the 24 metre squared area of canvas that's available. So I've got sort of 3 different shapes here, haven't I? 3 different side lengths. That one there, and we'll go with that one there. So I've got 4 sides. All right. So what are the dimensions of each of these sides? Well, the roof in yellow is x by y. So the area is equal to x times y plus my side lengths, which are x times x, 2 of them, plus the green backboard, which is again x times y. And all of those areas are equal to 24 metres squared of material. So that means, what have I got? I've got xy times 2 plus 2x squared is equal to 24. So that means y is equal to 24 minus 2x squared over 2x, which means y is equal to 12 minus x squared on x. So there's my relationship for y. So now this y value, which I'm going to highlight in green, I can now go to my rule for the volume and say it's x squared times y, which is equal to x squared times whatever y is, which is 12 minus x on x squared. So if I expand that now, that x, oops, that shouldn't be an x squared, it's an x. If I multiply the x squared through, that x cancels with that x squared, I get x times 12 minus x. Oops, I put the squared on the wrong spot. That looks better. So x times 12 minus x squared. So that's the rule for my volume. So volume is equal to 12x minus x cubed. So when does find the dimension of the shelter with chrome? When does a maximum occur? Need the maximum volume, so I need to know where the derivative dv dx is equal to 0. So dv dx is equal to 12 minus 3x squared. Solve that equal to 0. 3x squared is equal to 12, x squared is equal to 4, x equals plus or minus 2. Now, obviously our dimension of -2 makes no sense, so the side length must be 2 meters. So if the side length x is 2 meters, if I use my y relationship, y is equal to 12 minus 2 squared on 2, y is equal to 8 on 2, which is equal to 4 metres. So they're the dimensions of my box, or what are we making, a shelter, that gives me the largest possible volume. If I want to sketch this graph, if I come back down over here to the left, if I factorise that by taking x out, I get 12 minus x squared. So I get intercepts at 0 and plus or minus the square root of 12, which obviously is 2 root 3. I won't worry about the negative one because because of the wonderful things, because we only need x to be greater than 0, don't we? So there's my intercepts. If I want to know where my turning points are, I need to solve my derivative equal to 0, and my turning points, excuse me, my turning points occur at plus or minus 2. So there's one turning point up here at 2. So my graph would look like, I don't need all that stuff, and then in here, up to 2, and then I'm going to stop there as well because I can't have a negative volume. So different points of view, but I think at x equal to 0, if the x value is 0, it means we don't have a shape. So we're not going to include 0, and I'm not going to include 2 root 3. The maximum volume occurs when x equals 2. We haven't found the largest volume yet. So my rule for the volume, if I put 2 into that, I get 2 times 12 minus 2 squared, which is 2 times 8, which is equal to 16 metres cubed. That's my largest volume. And then the final question says, find the values of x and y for which the volume is equal to 10. So let's come up here for part C. I want to solve the volume equal to 10. So what's my rule for the volume? So that means I've got to solve 12x minus x cubed is equal to 10. X cubed minus 12x plus 10 is equal to 0. And I'm going to solve that on my CAS. If I type into my CAS, solve x cubed minus 12x plus 10 equal to 0 for x, I'm going to get x is equal to 0.892 or 2.93. Okay, so there are two possible values for that. So I also know that y is equal to 12 minus x squared on x, and if I substitute those x values in, that'll give me y is equal to, so we'll get y equal to, what do we say, 12.55, is that pair, or 2.93, 1.16. So both of those sets of dimensions will give us a volume of 10 metres cubed. All right, let's have a look at another one. Given that x equals, calculate the minimum value. So in this case, we just want to find a minimum. So again, even if I say, we won't call it value, so let's just call it polynomial, and that's equal to x squared plus xy minus y squared. Now we've got x and y, that's no good to us, so I want to rearrange this so that I'm going to write x equals 4 minus 2y from that equation there, and I'm just going to substitute that in for x. So p of x is probably a bad choice in the end. P of y is equal to 4 minus 2y squared plus the x value, which is 4 minus 2y times y minus y squared. So that 4 minus 2y, that was my x value that I've substituted in. We could probably use a CAS here, to be honest. Expand that, 16 minus 2 times 4 is 8, 16y plus 4y squared plus 4y minus 2y squared minus 2 minus y squared equals only 16 minus 16 plus 4 is minus 12y, and I got 4y squared minus 2 minus 1. So there's the polynomial that I want to try and get a maximum value for. So p dashed of y is equal to minus 12 plus 2y. The maximum occurs, y equal to 0. Oh, sorry, maximum occurs at dy dx equal to 0. So at p dashed of y equal to 0. So I get 2y minus 12 equal to 0. Y is equal to 12 on 2, which is 6. So if y is equal to 6, x will equal 4 minus 2 times 6, which is equal to negative 8. So the smallest value we get what's going on there? The smallest is at x equal to negative 8, y equal to 6, and that will be negative 8 squared plus negative 8 times 6 minus 6 squared, which is 64, minus 48 minus 36, which is what? Negative 48, negative 84 plus 64 is negative 20. So by rights, there shouldn't be any two numbers that you can think of that satisfy both of those conditions and give me a small value of negative 20. All right. Example 12. Typical sort of problem. We've done these sorts of problems before, but we just probably haven't used calculus to find our maximum and minimum values. Square piece of metal of side length 2 meters, 4 squares are removed. So from there to there is 2, there to there is 2, which makes this length here 2 minus 2x, because that's x. We've subtracted, we've cut out a side length of x from each of them. And that length there is also 2 minus 2x. So the volume of this box, volume, is equal to length by width by height, which is equal to, well, it's 2 minus 2x for the length, 2 minus 2x for the width, and the depth of the box is x. So if we now look to try and factorise where we can, let's get our pen back so we can say that the volume is equal to, if I take a 2 out of 1 minus x, take another 2 out of 1 minus x, and then I've got times x, so 2 by 2 is 4 by x, so I get 4x times 1 minus x squared, which is 4x times 1 minus 2x plus x squared. So then the volume is equal to 4x minus 8x squared plus 4x cubed, which matches off to what we had to show. So there's the rule for my volume, okay? So what do we need to know? We want to find the value of x that gives a maximum. So my maximums occur when the derivative is 0. So I need 4 minus 16x plus 12x squared equal to 0. So maybe if I take 4 out the front as a common factor, I'm going to put 3x squared minus 4x plus 1 equal to 0. So if I cross method, I'm hoping that's going to work. Negative 1, negative 1, looks about right. I get 3x minus 1, x minus 1 is equal to 0. So therefore I get x equal to 1/3, x equal to 1/3, or x equal to 1. So one of those two values should give me a maximum. Now, which of those values, if we think about the dimensions of my box is only 2 meters wide. So I can't then decide to make the little inset that I cut out 1 meter long, because then I'll end up cutting out, I'll have no paper left. So x equal to 1/3 is going to give me a maximum. As it turns out, x equal to 1 will give me a minimum, which happens to be 0. Show that the volume is a maximum for this value. So if I want to show that it's a maximum, I want to do a little sign diagram. There's 1/3 there. I want to pick a value to the left, say 0, and a value to the right, say 1, and hopefully the gradients will be negative, or positive and negative respectively. So if I put x equal to 0 into the derivative, if I put x equal to 0 in, where's my derivative? It's down here. I get 4 minus 0 plus 0, which is positive. So I get a positive gradient there at 0. Oh, no, I don't. Where's my derivative? Yes, I do. And then if I put x equal to 1 into my derivative, I get, well, I can't. If I get x equal to 1, I'm going to get 0, isn't it? So I'm going to have to pick a value like 2/3. So instead of 1, if I pick 2/3, I get 4 minus 16 times 2/3 plus 12 times 2/3 squared, which is 4 minus 32 on 3 plus 12 times 4 on 9. So if we look at these answers, I get, make them all 9, so I get 36 on 9 minus 96 on 9 plus 48 on 9, which is going to be a negative answer. So I get a positive gradient at 0, a 0 gradient at 1/3, and a negative gradient at 2/3. So therefore it's a maximum. Running out of room, I'm going to sketch the graph. And I'm going to go back to my factored form first, which is here, because that tells me I've got an intercept at 0, and I've got actually a turning point at 1, remember? So that's my x-intercept. Because it's a repeated factor, it's also a turning point. It's a negative cubic graph, is it? Where's my thing? No, it's not, it's a positive cubic. So my graph doesn't exist until I get to positive x. It goes up, goes down, and then it looks like that. But for a reasonable domain, we're going to stop there, because we spoke already about how my x value can't possibly be any bigger than 1, because I can't cut that much out of the paper. And that point there, we just decided was an x equal to 1/3. I've got to find out what the maximum is. So I better substitute that into V. So volume is equal to, up here on the top, is equal to 4 times 1/3 times 1 minus 1/3 squared, which is 4 on 3 times 2/3 squared. What's that going to give me? On 27, and I get 16 on 27. Do I? Looks pretty good. Find the values of x for which v equals 0.5 meters cubed. It's always run out of room. Let's come over to the left-hand side. That's a calculator job. So what value of x will give me a volume of 1/2 meter cubed? Where's my rule for the volume? So I've got to solve v equal to 4x times 1 minus x squared, and I want that equal to 1/2. So I'm going to go straight to my CAS, equal to a half, solve that, and that'll give me x equal to. And that'll give me x equal to 0.19, x equal to a half, or x equal to 1.309. So if we think that, what does that mean in the context of this problem? Well, if we had our graph extended the full way, and we want to know where x is equal to a half, it's a half, well then we've got answer number 1 there at, what is it, 0.19. My graph's obviously a little bit out. Answer number 2 there at a half, and answer number 3 there at 1.3. Hang on. That's that box question where volume is equal, looked like, y is at 1/3, 6, and what was the height equal to? $9 the height, the height is x. Okay, so just to clarify, just distinguish, we talk about absolute maximum, absolute minimum, maximum or minimum at an endpoint. Our local maximum and our local minimum really refer to our stationary points, okay? Not necessarily the overall maximum of the graph. So for example, I might have that graph there. So at this point here, it's what we call a local max, because in that isolated area, that's the maximum of the function, and we know by definition a local max refers to a stationary point or a turning point. The actual maximum of the function would be out here somewhere, because all of these values are greater than that maximum value there. In the same way, this point here is a local minimum, because everything down here is actually smaller than the function. So my stationary points aren't necessarily the smallest or the largest values of the function. They're just the local smallest or largest. If we want to know the actual largest or smallest, we refer to it as the absolute maximum or the absolute minimum. All right, so if we maybe rub out all that stuff there, and let's have a look at our graph where we've got a function that's defined over a particular domain, and we want to find out the absolute minimum value of the function. All right, so whenever we want to do an absolute, really, we need to do a graph. There's my graph, and we've got x squared plus 2, which is up here somewhere. So that's the whole graph. And we're interested in the graph between -2 and 4. So in reality, I've got to reduce this. It's maybe to look a bit like that. So at that point there, x is equal to -2. At that point here, x is equal to 4. So I can see straight away, without necessarily even finding a derivative, my minimum value there is at 0.2. This value here at x equal to 4, if I substitute it into the function, f of 4 is 4 squared plus 2, which is 18. So that's the point 418. And this point here is the point -2. Well, -2 squared is 4 plus 2, which is 6. So they're the key points. So the absolute maximum, and we can see, is equal to 18. The absolute minimum is, well, the smallest value of the function is 2, isn't it? Which means in reality, that's the information we need for our range. My range is from 2 to 18. And just to confirm, my domain is from -2 to 4. So I guess the key point there is my range isn't necessarily the values of the function at the endpoints. So that at the endpoint, the y value is 6 and 18, but the absolute minimum graph is at point 0.02. All right, we've got the graph of a graph restricted on the domain of -2 to 1. Again, find the maximum minimum values of the function. Again, absolutely normally we would go through finding some derivatives, but because we've got some graphs here that we should really know what they look like. There's a cubic graph with a point of inflection. That's the full cubic graph. I want to restrict it between -2 and 1. So let's work out f of -2. -2 cubed plus 2, which is -8 plus 2, which equals -6. So maybe let's restrict our graph, say there. So there's -2, and that's the point -2, -6. The other point is at x equal to 1. So if I put 1 in there, f of 1 is equal to 1 cubed plus 2, which is equal to 3. So my other points at x equal to 1 is the point 1, 3, and that's my point of inflection. Find the maximum minimum value of the function. So clearly we can see the maximum is 3, the minimum is equal to -6. Let's just refresh example 12 to graph 15 on 27. All right. In example 12, the maximum volume of the box was found. The maximum value corresponded to a local maximum of the graph of blah, blah, blah. This was also the absolute maximum value. If the height of the box must be less than 0.3 metres, what will the maximum volume of the box be? So if we remember, if we sketch the graph, something like that, and then it would have gone up like that, all right? And the actual maximum, so the maximum value there was at 1/3, 6 on 27. So we need the height of our box. So this is x, and this is v. All right, so don't forget from that previous example, there was a relationship between the. So at the moment, if we have a look at our coordinates for the maximum, my height is equal to 1/3 and the volume is equal to 6 on 27. Now, obviously 1/3 is 0.333. So it says that my height has to be less than 0.3. So that means that my height here, the x value, has to stop here at 0.3 somewhere. Okay, so clearly my maximum is actually going to occur. So since the height is less than 0.3, the maximum, we're saying less than or equal to, the maximum occurs at v of 0.3. In other words, if I substitute 0.3 into that rule, 4 times 0.3 cubed minus 8 times 0.3 squared, 4 times 0.3, and that's equal to 0.588, which is actually 147 on 250. Okay, so it's just really being clear in your head about an absolute maximum or a maximum value if we have some constraints placed upon us. All right, off you go.